We will review chapter 5, the DC to DC converters. This is for course EL 4242, Power Electronics. We'll review, I strongly recommend that before you review this video, you review these MathCAD files, the video for MathCAD files for the worked out examples in this chapter. The one is the basic fundamentals of DC to DC converter, like a step up. Suppose you got a switch, it's an electronic switch. Then once we close the switch, the output voltage will be the same as the input voltages, and then the current will be the V by R, Vs by R. That the shape of the voltage and current is the same. Like the T1 is the on time and T2 is the off time. The T is the period, how often you turn on the switch. And then we can find out that show the average voltage, our average voltage will be equal to K times the Vs, and the root mean square value, which is the 0 to Kt, V square dt, square root, and then root square root of K, square root of Vs, and then the power will be on the load V square by the VOI. You can show that this will be V square by the Bs square divided by R is the normal power divided by the K. That means the K is the duty cycle. By varying the duty cycle, one could vary the output voltage from 0 to Vs, and then also the power from 0 to Vs squared by R. If you keep the switch completely on, this will be the maximum output voltage and the maximum power, but you can vary in between them. This is the key principle of that, the DC to DC conversion. Now this is this. Let me go to the next one. Now, what is happening? The effective resistance. Did I miss something? Effective resistance is like this. The effective resistance, like what is happening, like this, the switch acts like a modulator. Once you connect that completely, if you connect the switch completely, it will be the resistance is R. Okay. If you take the switch out, the resistance seen by this, like if you look to the battery, this battery sees a load resistance over R if the switch is closed. But if the switch is completely open, that the battery sees like open circuit infinity. That means that resistance seen by that battery Vs is like this R by K. R by K is the resistance. Is that the K is equal to 1. That is the complete one. If K equal to 0, the switch is not on for any time. That is for duty cycle, the switch offers an effective resistance as the R by K. This is the right answer. Like it's like a modulator. It's like a variable resistance. As far as the source is concerned, the variable. RMS value of the output voltage, you know that. The duty cycle is 0.5, Vs is 200. You can find the RMS value of the output is basically 25 K times the 200. Okay, please do the calculation. It's a simple one. The average value of the output is simple, that we say the K times the Vs. If the K is 25% of the Vs, it will be is the K times the Vs. This is the average output voltage. If they ask for a question, you can find out the question also. The duty cycle. If R is equal to that, you can find out if the R is that, Vs, the average duty cycle is that, and the average source current is that one. The duty cycle, the average, the current through the source is, the average current from the source is like the Vs. You can find out the average current of the supply is this source current is the same. You can find out how much will be what is the duty cycle for that. Yeah. And you know that if there's a resistance there, the V by I, once you know the output voltage, you can find the output current, and then the current is given, you should be able to find that how much was that the duty cycle. One of the very concept is the modulation index. What is a modulation index? Suppose we have a comparator. We have a comparator with a triangular wave, and then another one with this DC signal there. Now, if you compare the the triangular wave with the DC signal, then you can say the intersection of them, and intersection will be Vs, the KT. Now this one will be the KT, the percentage of time the switch on. The duty cycle will be the duty cycle of that one. What it means by having this, the DC voltage, like if this is the maximum is 10, if this is a text maximum, and if this is 5, you can say duty cycle 50%. On the other hand, if you make the VCR equal to 10, that will be all 100%, K will be almost like on 1. And if you make VCR equal to 0, this will be 0. That means that the duty cycle is the VCR divided by VC. The VCR, this is the VCR divided by VCR is the maximum value you can have divided by the VR. That is the modulation index. That ratio of that, this divided by the maximum one is the modulation index. Now increasing the modulation index will cause the duty cycle what? It will increase the output voltage, right? So increase modulation duty cycle will increase. If you make the DC voltage, it will be increased. Okay. Increasing the modulation index will increase the duty cycle. Like the one of the situation is what very often happen that you have an inductor, the load with the inductor R and L, and often a battery maybe, you know, if there is a motor, the DC motor, but just to put this in generalized case, R, L, and E. And then if you switch the turn on the switch that we mentioned before, the current will be rising. The current will be rising. The current will rise. The output voltage will be, output voltage will be like the DC. The current will rise, assuming the inductor, is pretty much linear. And then when the switch is off, and then the switch off rise from the under steady state. In the first cycle, it will go like this, but eventually it will steady state. And then when the switch is off, then it will be freewheeling. That freewheeling there, the current will fall there. Now, as long as the current will rise from minimum to the maximum, and the minimum maximum under the steady state I1, and this is the I1 is the minimum, I2 is the maximum, that will be steady state, that will come to the same value. Whatever started, what will finish on the steady state continue. But if you have like a battery is too much battery voltage, or the inductor is not enough, that will fall very fast, and then it may be discontinuous. That could be continuous or discontinuous. As long as it's a continuous, that if I1 is less than or equal to 0, that's the critical value of that inductor you need. Now I1 you can, for as long as a continuous gain, you can find out the I1 by this expression you have in the book there. And then also I2, the maximum value, you can calculate it out. The Vs is normally given, R is normally given, the K, and then the R and the inductor ratio, the K to duty cycle, you can find out that the minimum and maximum, the values of that of the circuit. Now that one of the issues is called the ripple. That's the ripple of the DC. The output voltage, the current output voltage has a ripple that is varied. If you would be using a DC motor, that there will be the current will be fluctuation, and that the motor torque may be changing. As a result, you want to make, maybe you have to have an extra inductor to smooth the current. Like the ripple current, you can show that ripple current between that ripple current I2 by I1. You can calculate or show that this is the tangent function of that. But normally that function is the R by 4F is normally small. You can pretty much, like you can say that tan of theta is approximately equal to theta as long as that is a small value. And then becomes that is Vs divided by 4FL. That means that if you have that to same amount of the ripple, if your inductor is high, if you make the inductor high, that the ripple will be less. That if your frequency is high, that will be less. You can have if you can increase the frequency to very large, that for the same amount of ripple, you can make the inductor very, very small. That's why the ripple factor will depend on the inductor only. No. The switching frequency, no. It will depend for both of them. It will depend on that supply voltages and the frequency and the inductor too. Load battery. If you have increasing the load battery, will cause this current to be discontinuous, more towards discontinuous. If you make this battery make more and more, that will be locked. If you make this battery, it's a no battery there, it may be like a continuous, right? It may be continuous. But if you make the battery more and more, it may be towards the discontinuity. It may be discontinuity, more and more discontinuous there. And then it may be towards more discontinuity, and that if it is a battery is none there, it may be continuous. This is this zero there, this is the I of the load, and it may be discontinuous. That's why increasing the battery will cause the load current to be more towards the discontinuous. Minimum steady state load current, you should be able to calculate it out. This is a particular example. The Vs is given, Vs is given, R, L, and E is given there. The key is 0, K is given there. You have been asked to find the minimum steady state current I1. You should be able to calculate it out. How much is that? And because you know that equation, you can find out how much is the minimum, the current would be like this. The maximum peak current, similarly, they ask you that this Vs is no, and L is given, R is given, E is 0, the duty cycle given, F is given there. You should be able to find I2. There are some examples in book, and then use the math files to calculate out. The switching frequency, they ask you if this one, the ripple frequency is capped to the peak ripple voltage to 1 ampere is given. Remember that the peak value is given, like a delta I is given, is a maximum is given 1 amp. They ask you how much this V supply is given, the inductor, L is given, R is given. They ask you what should be the frequency, should be the cap to ripple with approximately close to that one. What frequency should be? That's asking. The switching frequency, the question comes here, and if the switching frequency double, and the load inductor is double, the peak-to-peak ripple voltage will be approximately become multiple of the following factor. What is that one? Remember that if you increase the frequency, that the Vs divided by 4FL. If you increase it to 2, increase it to double, that means it will be what? 1/4. It will become 1/4. It's not that half. Okay, it will be it will be multiple of the following, and become a multiple of the following. It will be 1/4. It will be much less because of the double for 1/2 for frequency, 1/2 for inductor. The transfer power. One of the important things to know that one could transfer a power from a low voltage to the high voltage. For example, like if you have this switch, the closed, if you close the switch there, if you turn on the switch, the current will flow. You got a battery there. This will be Vs times the L times the T. This will be current will flow through this one. Now, when the current rises, you decide when you want to stop it. Once you stop the current, suppose it rises to the current I1 or I2, it reaches an I2. Then when you open the switch, inductor has some energy, half L I2 square. This energy has to go some places. It's going to induce the voltage and force the power, the energy go from that battery to this, the Bs to the E. The question asks for you, what is the condition for that one? That there is the equation there that basically that Vs must be lower than that E. Okay, if this is 100 volts, that must be less than 100 volts. You cannot transfer from high to the low. You can transfer from low to the high. That's the beauty of that. You can step up a voltage. Step up DC voltage. That's the basic concept of that one. If you have an inductor and a switch and that battery there, you turn on, the current rises. When you turn off, the current falls there. And then you can show that as long as the continuous there, the minimum current and the maximum current and the ripple, you can calculate it out from there. This basically you have an inductor. If you got an inductor there, you got a switch. You close this switch, and your energy current flow build up through the inductor, and the inductor current build up, and energy stored in the inductor. When you turn off the switch, the inductor energy goes through the diode to your load, and that the battery supplies energy to the inductor transfer to that the load resistance. This is the basic concept of a step up conversion. Current through the inductor, What will be the current through the inductor? It will be rising almost like a linearly, because this is like a short there. You got a short there. The Vs equal to L di dt. That's basically, that means equal to I equal to Li di dt is equal to Vs by L, and that I is equal to Vs Lt. That will be linear. The current rises almost linearly. Current through the inductor when the switch is open. When the switch is open, the current through the inductor will fall exponentially, pretty much exponentially, because the RL circuit with the battery there, they're going to fall pretty much exponentially. Now, minimum steady state load current, they are giving a particular case, asking your Vs is given there, free and the L is given, F there is there, and the duty cycle is given, the frequency is 1 kilohertz. The minimum steady state in the range of, you are asking to find the U1, you should find out the U1. But remember that U1 cannot be negative values. U1 cannot be negative values, okay? It could be that if it is not within there, it could be not a negative values. It could be positive, or it cannot be negative. Please do the calculation. And the peak one is similarly the peak value. What is that peak value? We mentioned to you when the current rises and current falls, they're asking for the I2, and then ask for that the peak value. The peak is not a limit there. It could be anything there. Okay, they ask you what is the value, whether this is there or any of them. Please do the calculation. The buck converter. The buck converter is a step down step. Buck is the name, it says the step down converter, but this is the converter. What it happens like, it is like on the output side there is a filter. There is a filter there. What it happens that you got a capacitor fit in there. Once you turn on the switch, the current comes through the inductor, and then through the capacitor to the load you supply the voltage there. Now what happened that when you turn off the switch, there will be a freewheeling diode will stop that. Between L and C, they're acting like a filter. The L and C acting like a filter there. When you turn on the switch, inductor current will rise, and then the capacitor voltage will rise, and then this, when you turn off the switch, the current will fall. Okay, current will fall, and the battery voltage will also, when you turn off the switch, there will be freewheeling there. The capacitor voltage will fall, and then also supply, the capacitor will supply to the load, and the voltage will fall. What is happening? The buck converter, the energy transfer from the to the load is done. No media, directly transfer from the load, because this is a load here. This is a load. This is the load here. You directly, when you turn on, you supply to this load, a power to the load. There is no inductor or any other source. But other device, other converter, you're going to see there is a media there. You apply this. This is the load. This is the filter. Is a part of the load. You apply, you close the switch. It directly apply power to that the load there. No media, direct transfer energy to the load. The boost converter. There is a boost converter here. What is a boost converter here? That boost converter, when you turn on the switch, that the inductor current will rise, and then when you turn off the switch, that the energy stored in the inductor transfer power or energy through this diode to this load here. This is the load here. That means in this case, the battery, the energy when the transistor is switched, energy is transferred from the supply to this inductor, and inductor transfer the energy to that load there through the diode there. That's why in boost converter, the transfer energy is to the load is done through the media inductor. That inductor is the energy transferring element to that to the load. Let's go to the next one. The choke converter. There is a choke converter there, and that what it does there. That look what happened there. If you go and do nothing, you turn on the supply. You turn on the supply. If you turn on the supply, there is a inductor, load, a capacitor, inductor, capacitor, and the diode. The capacitor will charge into this direction. The capacitor will remain a charge into this direction. Once it charged into the direction, what happened that when the current through the from the inductor, the capacitor also charges. Now, next time you go there, and then you turn on that switch. Once you turn on the switch, the one current flowing through that, through this L1, and that means that inductor is getting an energy from that the source there. Now what is happening there? That the capacitor now has a voltage. Now capacitor will now which will give now energy to the load. Capacitor now will be giving a energy to the load there. It's giving a look at that, giving energy to the load is supplied to the load. And then when it happens now, next time you turn it off, when it takes over, when it does, that capacitor voltage will fall. That inductor current rises, capacitor voltage now falls, capacitor voltage falls, inductor current rises, capacitor voltage falls because it has to supply energy to that load. And then next time you turn off the switch, the inductor again current will fall, the inductor current fall, the capacitor voltage now in this case capacitor will fall, capacitor voltage now will be rising. It was falling, then it will be rising. Okay, it will be falling, and then that means that when you turn on the switch, inductor when you turn off the switch, this C1 gets energy from the inductor. When you turn on the switch, then this inductor gets energy from the battery, so the source to the inductor. Inductor, the source transfers to this inductor L1. L1 give it to the capacitor. Capacitor give it to this load. That's why in the choke converter, the transfer energy from the VS to the load is done through the media capacitor C1. C1 is the media transfer. And as a result, the capacitor will have the voltage will be positive, voltage will be negative, and the current sometimes will be positing this way, sometimes will be positing this way. The capacitor current will be AC, alternating. You got a DC current, and one time you got a positive direction, another current is a direction. This capacitor has to take all the energy and transfer to take it and give it back. Like the operation of a motor. Like the question is, reverse operation of motor will depend on reverse. You want to reverse this motor. You want to, if a motor is working as a reverse motorization, you want to have a positive and reverse, opposite direction. If you enter opposite direction, then and you want to operate in the third quadrant. First quadrant, this is the V and I. The VL and I, the first quadrant will be equal to VL positive, and I is negative in the first. Sorry, this is the one. I don't know what you call it. This is the one you want to make sure the third quadrant. The V1, VL will be positive, and the IL will be negative. The VL and then IL, and that you want to make sure that the VL is positive, okay, and then also the first quadrant will be, the fourth quadrant will be first quadrant, second quadrant, third quadrant, and then fourth quadrant. Now what you want in this particular case, this one you want the voltage to be positive, and then that this is the one reverse operation of the motor in the forward direction. In this, if you want this one, it should be VL should be negative and the IL also negative. What you want, the current should be flowing in this direction, and the opposite direction, normally current will be this direction, and then the normal voltage will be positive and negative. You want that to be current to flow this direction and the voltage to be opposite direction. That means it should be both, that current and voltage should be in opposite direction. That means the voltage should be, like if you would be voltage should be this direction, that means voltage should be opposite of what it should be, and the current should be also the other direction. That means it should be VL should be negative, and also the IL should be negative. Both will be negative there. Forward regenerating mode. The forward regenerating mode, if you would be the switch of this forward regenerating mode, then if a motor can be operated in the regenerative braking mode after being forward mode operation by modulating the switch. Like in the forward direction, you got an S1, the current flows are that, and then S2, this is the forward direction, current will move through that. Now what happened now, this switch is on, this switch is on. Now what happened now, if the current is flowing this direction, okay, current is flowing this direction, then you have your voltage direction. What happened to this, if you want um, to regenerate, you want to mode this regenerate, you operate the diode when your motor is off, when the motor, no, motor has the battery, it has the motor is running as a generator, is that what you modulate, you operate the switch. If you operate the switch, look at that, if you got even a one, if you got a 1 volts or 2 volts, small volts the motor has, and then you switch on S4, then it's going to current will build up. Once your current build up, once the current build up through that, once the current build up, current rises, and once the current rises, you turn off the switch. That current has to go through that. It will go through the D1, and then come through that, and then come through that. And if the switch is there or diode, it will be regenerating back to the ground. Remember, we mentioned that you transfer from this low voltage to the high voltage. That will be that. That means the switch S4 of the DC converter. That please read that book, to get that four quadrant operation what you do. One of the most important things that happen in power electron is the power factor is a very important thing. And if you have if you're taking 100 amps, and if you got a 120 volts, and then if your power factor is like a 1, you're going to have a power will be the voltage times the power factor. That will be 120 times 100. What happens if your power factor is 0? There is a load, the power factor is 0, like inductive load, completely inductive load. If the power factor is 0, the power will be almost 0. That's why there is a tendency to have a high power factor. You are drawing a current at a certain voltage, the power you are consuming is very small, and that is not desirable. And then most desirable to have a unity power factor. What you do, there is a what you do, you just have a techniques unity power factor. You got a rectifier. If you got a rectifier here, you try to make sure the inductor current, this is the current here, if the inductor current is sine wave, that this current is sine wave, that means that will be also pretty much sine wave. That means that what happened that this this switch is turned on in such a way that this current become a sine wave. What it do is basically you got the sine wave, and you on and off, 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 on and off. You follow a reference current. You follow a reference current, and it's a reference current, pretty much a sine wave. Okay, pretty much a sine wave. Then you look through a DC voltage. You got a DC voltage. You want to have a, so you got a 10 volts here, and you have a 10 volts reference. Maybe it is a 9 now. You want to control that. You got a controller. You got a voltage there. Then you have to have this the current here. You want this current to be sine wave. You want to monitor that is this current. You want to be sine wave. And then once you have a sine wave, then you put this MOSFET on the switch to turn on and off, so that you have a sine wave reference in there. This one, you want to maintain what the question are, to obtain a unity power factor, the modulation is, the transistor is modulated at high frequency to produce half sine wave, that is absolute value of sine wave. That is, this part is a sine wave, this is a half sine wave, absolute sine wave, so that the input side of the rectifier is a sine wave. That's basically absolute value of sine wave. Like if you got this sine wave, or you got an absolute value of sine omega t, that will be half sine wave. That's basically the answer. You want to make sure that this modulating a half sine wave. The input current. Now what happened that if you have a current here, that input current here, if you got here, if your input current look through that, it's a pulse there. You got a pulse there. As a result, the input current will have a lot of the harmonic spectrum. If you do the Fourier analysis of this waveform, you got the harmonic analysis. If you look at the book, that means the input current is a pulsating DC waveform. It's a DC unidirectional, but it's a pulsating. The input current is a DC, but it's a pulsating DC waveform. As a result, to get rid of that, the pulsation, or you apply a filter. You use normally a filter, so that if there are a lot of harmonics, if you got a lot of the harmonics factor there, you got some sine wave, some different sine wave. The frequency AC component, the high frequency component will go to the capacitor, and then that higher the impedance of an inductor is equal to j omega L. The impedance of a capacitor is equal to j omega C. Like what happened that if you got a frequency is high, the ripple frequency or the harmonic frequency, the inductor here impedance will be large. It's like a 2 phi f. If the higher frequency, this inductor will give a high impedance, so that they cannot flow through the supply. It cannot go through that. On the other hand, if the frequency is large, the capacitor will provide a low path impedance, and they will flow through that, rather than it will prevent it not to go there and also go through the capacitor. That's why passes this. What happened that input inductor LE passes the DC component, DC supply side. Only the DC can go, not that the frequency dependent. Input side inductor. Inductor also, in the input side, it's not an inductor, it's a capacitor. The capacitor passes the high frequency component to go. The high frequency will go through it, the DC component will go through it as well. Okay? And that's why this is the input side capacitor passes the high frequency component through the capacitor. I think that's the end of that. I again remind you, please review that, the MathCAD the video files, and run those problems, work out examples in the book. And you don't have to do anything. There is a video how to do that. You don't need any software. The UWF have the software. I think. Thank you.